Alright, this is our second lesson in the log unit, and today we actually get to the logs. Hooray. Uh, 7.2, it's a little tricky, but you're going to do great. So earlier this year we talked about inverse functions. So for most functions, or for a lot of functions at least, you can find an inverse to that function. We found earlier in this year, and it was way back in Unit 1, we found inverses for lines, for quadratics, for square roots, for cube roots, and if you graph a function and its inverse together on a coordinate plane, you can see that a function and its inverse are mirror images of each other, and we talked about that way back. So here we have function f of x, which happens to be a line. If we found and graphed the inverse of that function, it would be this blue line, f inverse of x. If we had this, this happens to be a square root function over here, f of x. If we found the inverse of that and we graphed it, it would be this function here, which is a quadratic. That's f inverse of x. So that's from way back in Unit 1. Well, last time in class we looked at the graph of exponential functions, and one of the graphs in particular that we graphed was f of x equals 2 to the power x. So here on this coordinate plane we see the function f of x, and it is kind of that bluish purplish color. Uh, that's function f of x, which we graphed last time. And you can see this table goes with it. If x is -1, f of x is 1/2. If x is 0, 2 to the 0 power is 1. If x is 1, 2 to the 1 power is 2. If x is 2, 2 squared is 4, and so forth. So that's a table that goes with f of x. Well, if I reflect it and look at this inverse function, f inverse of x, you can see the shape of that graph. And the table, if you remember back to when we talked about inverses, the table of f inverse of x sort of switches the x and y values. So for f inverse of x, if we put 1/2 into the function, we get the answer -1. If we put 1 into f inverse, we get 0. If we put 2 in for x in f inverse, we get 1. And it sort of switches those values. So we can see f inverse on this graph. My question to you is, what is this function, this inverse? What is it? What's the inverse function of an exponential? Well, if you think back to Unit 1, which you may or may not remember very well, but if you think back, way back, if we wanted to find the inverse of a function using algebra, I mean, we just saw a visual of it, but if we wanted to do it sort of algebraically, one of the procedures we could use to find that inverse would be to switch the x and y and solve for y. So let's try that to find our inverse. Our original function is f of x equals 2 to the x power. We could rewrite that so that this f of x becomes a y. So we have y equals 2 to the x power. So now we're going to switch the x and y. So it's x equals 2 to the y power. And now we just need to solve for y. Or, yeah, solve for y. So if y is in the exponent position, how do we get it by itself? And you might have a couple of ideas. Sometimes people think, well, maybe we could divide by 2. Well, if we have 2 to the y power divided by 2, ooh, that doesn't really help. That would be helpful if we had 2y, but it doesn't really do much when it's exponential like that. So dividing doesn't work. Sometimes people think maybe I could take the square root of both sides of my equation. Oh, that didn't really work. That would work great if the thing we had is y squared. Taking the square root would be perfect in that case. It doesn't help us with what we have, though. Maybe you can think of another idea. the bottom line is that you don't really, unfortunately yet, have a tool to deal with this equation. We need maybe a definition to help us. So we're going to say that if we have something like x equals 2 to the y power, we're just going to define y to be the log base 2 of x. We're going to call that operation, if you will, to get the y by itself logarithm. We're going to define logarithm to be the inverse of exponential. So we can't really algebraically find the inverse of x, but we could define it to be the log base 2 of x. So what the heck is a log? Well, a log is really just the answer to the question, what power is required to go from a base of b to reach a value of a. So if we wanted to know what log base 2 of 8 is, another way you can think about it, according to the definition that I showed you, is you're really trying to answer the question, what power would I need with base 2 to get the result 8? Log base 2 of 8 is saying, hey, what power will take me from base 2 to 8? And hopefully you know that 2 to the third power is 8. So if my question is what power would be required to get from base 2 to 8, the answer is 3. Log base 2 of 8 is 3. Let's look at a couple more of these because I think sometimes once you just think through a few of them, you really get the hang of what these logs are. So if I want to know what's log base 2 of 32, I just can think to myself, well, what power would I need? I have a base of 2. What power do I need to get 32? Well, the power would be power 5. So the answer is 5. A logarithm is just a power. It's finding what power you would need. Log base 2 of 1/8. We're sticking with base 2 for a minute. So that's saying what power of 2 is 1 over 8. Well, if you look just above, it says 2 to the third power is 8. But this 8 is in the denominator. If you remember correctly, let's see, if we have a negative exponent, that would switch it down to the denominator. So this one happens to be negative 3. Log base 2 of 1/8 is negative 3. We're going to switch to another base because logs, like exponentials, can have lots of different bases. This next one happens to be base 5. So if I want to know what is log base 5 of 25, I'm thinking about what power of 5 is 25. And the answer, I think you probably know, is that it is the second power. And then one last one, 3 to the power 243. Sorry, I don't know how I just read that. Log base 3 of 243, we would be thinking 3 to what power is 243? And the answer, you may have to test out a couple of things in your calculator, but I think, oh, where's my calculator? I'm pretty sure it's the 5th power. Let me type it and make sure. 3 to the 5th power, 243, that's right. So this one was 5. So again, when you're thinking about like what a log is a power. You're trying to figure out what power would be required to get from that base, whatever the base is, to that argument. Okay, so I want you to try a couple. If you get stuck on one or two, it's okay. Just try them out, see what you can do. Pause your video for a second and then check your answers and I'll tell you the solutions. So if you're doing log base 3 of 9, you're thinking what power of 3 is 9? It would be 3 squared is 9. Log base 2 of 16, we're thinking about 2 to what power is 16? That would be power 4. It's like logs are the inverse of exponential. It's like doing exponentials, but thinking about them backwards, because it's the inverse. Log base 4 of 64, what power is required to go from base 4 to 64? That would be 4 to the third power. Log base 7 of 7. We're thinking 7 to what power would give me the answer 7? Hopefully you can see that the answer is 1. Couple more. Log base 9 of 1. We're thinking what power of 9 is 1? Well, if you think back to your exponent rules, the power that gives you answer 1 is 0. This one is 0. Log base 2 of 2 to the 8th. We're thinking about 2 to what power is 2 to the 8th? I love to write that one down because when you write it that way, people almost always immediately see that the answer is 8. One last one, log base 5 of 1/5. Well, log base 5 of 5 would be 1, but the 5 is now in the denominator, so we need a negative power here. Negative 1. 5 to what power is 1 over 5? We need a negative 1 power to make that happen. So oftentimes, it is very handy to convert between the two forms. This is a method we'll use on 7.5 when we are solving logarithmic equations, but these two forms of equations, this log equation and this exponential equation, they're really the same thing. They're just two different forms of the same relationship, two different ways of writing it. So we can convert back and forth between the two. If we have a log equation, we could just as easily write it as an exponential equation, and sometimes we want to convert that. So if we have log base b of hat, it's base b here, equal to camper, another way of writing that exact same equation is to write it as an exponential. If the base of the log is b, the base of the exponential is b. And remember that logs and exponentials are inverses. So the input becomes the output, and the output becomes the input. They switch because they're inverses. So if we have a log base b of hat equals camper, another way of writing that exact same equation is to say that b to the camper power equals hat. And maybe it's weird that I'm using words here, but the reason I'm using words is because sometimes these placeholders are little expressions or things, and it's handy to maybe think of it as not just one letter. Just like we can turn a log function into an exponential function, sometimes when we have an exponential function, we want to rewrite it as a log. So if you have an exponential function that is base b, you can equally well write that as a log base b. So base is b here, and if the exponential is b to the happy power equals kelp, it would be the log of kelp equals happy. The input and the output switch because the two functions are inverses. Okay, so we can convert back and forth between those two forms. Let's try rewriting a couple. So if we have a log, we could write it as an exponential. A log base 3 of 9 equal 2. That is exactly the same. It's giving you the exact same information as 3 base 3 to the second power equals 9. Two different forms of the same equation. Two ways of describing the same relationship. Log base 8 of 1 equals 0. I couldn't write that as an exponential. It would be base 8. 8 to the, and I just need to switch these two, 8 to the 0 power equals 1. Let's try going the other direction. If I have an exponential, can I write the log? Now this one, for some reason, is trickier for people. I think the reason it's trickier is because you have to remember, I have an exponential, I'm writing a log. People sometimes forget to actually write the word log there. So I have a log. Base is going to be the same. It's going to be base 10 of, and I want to switch these two now, of 1,000 equals 3. So we switch the 1,000 and the 3. And let's try one more of those. I have an exponential. 5 to the negative 2 power equals 1 over 25. I want to write it as a log. So I write my log. The base is going to be the same. It's base 5 of, and I need to switch these two now. Log base 5 of 1 over 25 is equal to negative 2. So I'm switching that. The base is the base. I was switching this. The base is the base. Okie dokie. So that's rewriting. All of the logarithms we've looked at so far have been sort of nice ones that we could maybe figure out in our head, like log base 10 of 100. So we're thinking what power of 10 is 100, and hopefully you know that that would be 10 squared, second power. And log base 10 of 1,000, we're thinking what power of 10 is 1,000? That would be power 3. 10 to the third power is 1,000. But what if our log is not such a nice answer? Log base 10 of 542. How could we figure out the answer to this? Well, if 542 is between 100 and 1,000, our answer is going to be somewhere between 2 and 3. Somewhere in between there. Maybe it's 2.5. Is 10 to the 2.5 equal to 542? And if we tested that, maybe we'd be like, let's see, 10 to the 2.5 power is 316.23. Well, it's kind of close to 542. Maybe a little bit bigger number, maybe 10 to the 2.8 power. That's 630.96. So that's also kind of close to 542. It looks like it needs to be in between those two powers somewhere. Well, I know the answer. The answer is 2.734, and you could test it. 10 to the power 2.734 is 542.0009. So that's really close to 542. So how can we come up with this 2.734 number without guess and checking our way into oblivion? Well, it turns out your calculator knows some logs. It knows a few. There's two bases that are the most common, and the calculator knows those two bases. Your calculator knows base 10. And you'll see that on your calculator on that LOG log button. This in some ways is like having a square root or an x. We know a square root is a root 2. We know if we have x, it's 1x to the power 1. Sometimes numbers don't get written because we understand them to be there. When you see an LOG log, we are assuming that we all know that it's base 10. So you don't see the little 10 base next to it, but on the calculator button, but an LOG log is base 10. The other log that your calculator knows the base of is the natural log. So natural logarithms are base e, and your calculator, when you have a log with a base of e, it uses the notation ln. That's a letter L and a letter N. On the calculator, I guess it is uppercase, but usually in math textbooks or things you see lowercase. So when you see that ln, like if I had a thing that said ln of 5, you have to understand that it automatically, I know because of the notation, I know that is base E. And by the way, it is not 1n, it is not in, it is ln. The L is for log, and the N is for natural, and except sort of Latin-y. But when you read it, you should say natural log of x, or natural log of 5, but some people do say ln of 5 or ln of x, but it's more proper to just say natural log. Okay, so we want to practice evaluating these. Essentially, I just want you to get used to the position of the button on your calculator. So if we want to know what the log of 7 is, we just use that log button on the calculator. Real quick, if you're using a TI calculator, the button is right here. So we type in log 7, and our calculator says that that is 0.845. And remember that the base isn't written. So you have to remember that that is base 10. Sometimes it's important to remember what that base is. We want to know the natural log. So remember ln is the natural log. It's base e, which your calculator knows. If we want to know that, it's the button below the log, the ln button of 0.25, I think it was. And that would be negative 1.386. Negative 1.386. The next one, the log of negative 3. We can type that on our calculator, log of negative 3. Hit enter, and our calculator says, hey, that's a non-real answer. It's like an error. It's not part of the domain of the log. Don't panic if you see error. It's the same as when you get an error from a square root or something. Often it means that the answer is imaginary, or sometimes it's just simply not defined. You can write, let's see, let me go quit. You can write error if you want. You can write no solution. There's not an answer to this problem. And remember that this is base, log is base 10. And the last one is the natural log of 50. If we type that in, our calculator tells us that is 3.912. And remember that that would be, it's a natural log, it is base E. Here's the guy that invented logs. He invented logs to make math easier for mathematicians and for scientists. There were no calculators, and logarithms made them a little bit faster. We talked a lot about it in class, and you missed out because it was awesome. He was just trying to help, and he did help. Places that logs come up in real life. Music notes. If you consider the different notes and the frequency of the vibrations that make those notes, it's a logarithmic relationship. The Richter scale for earthquakes, when you're talking about the magnitude of the earthquake versus the energy of the earthquake, that is a logarithmic scale. Measurements of sounds, when you talk about the number of decimal, sorry, not decimals, decibels of a sound and the intensity of that sound. That's a logarithmic scale. Star magnitudes measured logarithmically, and when you cram, this is showing you a Richter scale. Another one is pH. The pH scale for measuring how basic or acidic a solution is, that is a logarithmic scale. The pH is the negative log of the hydrogen ion concentration. It's kind of interesting because sometimes people think, oh, between here and here, it's 4 times more acidic. But it's really not. It's 10 to the 4th times more. Oh, that's actually basic. But anyway, it's not 4 times more basic. It's 10,000 times more basic. It's a logarithmic scale. All right, so finally, we're just going to look at some graphs of some log functions, and that will be it for today. And the rest of the unit, we will be focusing on logs. So remember, logs are the inverses of exponentials, so the shape of the log is very much connected to the shape of the exponential. That little one above shows the shape of exponentials. Remember, we graphed those in our last class. They have an asymptote that is horizontal, unless it has some sort of vertical shift, vertical translation. That asymptote is at 0, and it's a horizontal asymptote. And the function on the, I know my right from left. On the left, it's really, really close to that asymptote, and then it just grows, and at first it's not growing very fast, and then it kind of takes off and grows really fast, grows exponentially. So that's what an exponential graph looks like. And remember, the curvature of that exponential function depends on the base. Well, logarithms work kind of the same way when you're graphing them, but they're the inverses. So the asymptote, instead of being horizontal, because it's the inverse, the asymptote is now a vertical asymptote. So the function is really, really close to that asymptote down there on the far left side, and it kind of goes up, and then it kind of almost levels off, but it doesn't. It does. These two keep growing. They will continue to go up. They just grow very slowly. And again, like with exponential functions, the base of the log will just tell you more information about the curvature. Smaller bases like base 2, base 1.5, those ones, that's like this red one and this light blue one. There's sort of a wider curve, and then as that base gets higher, that curve gets a lot tighter. So base 10 would be this green one. We are primarily going to graph logarithmic functions with base e. Like with exponentials, I told you we were going to focus on base e exponentials. We're also, as far as graphing goes, going to focus on base e logs. So we're going to be using that natural log button as we're graphing. Now we could graph other bases, but we're just mostly going to stick with base E. Transformations with logarithmic functions work the same as with other types of transformations, with other types of functions. So if it has a number added to the end, a constant, that is a vertical shift. That is going to shift it up or down. Two ups. If it has a value with the x, that is going to shift it left and right. And in fact, because these things have normally, if there's no shift, a vertical asymptote right at 0, if you shift it left or right, that asymptote would shift left or right. And we'll talk about that as we look at some examples. And then finally, if you do have some sort of constant here, that's a vertical stretch. And so maybe instead of growing like this, it grows a little faster because it's doubled. Or if it's negative, you know, instead of looking like this, it would flip that shape over and it would look like this. Make sure that you show the asymptote as you're graphing. So let's look at a couple of graphs. First of all, I'm just going to put the natural log of x in just for funsies so we can talk about a few things with the calculator. When you type in your calculator natural log or regular log, log log base 10, it automatically puts this parenthesis here for you. So whatever function you're doing, make sure you tell the calculator where that grouping ends. So this one's not in your notes. I just want to very first show you natural log of x on the calculator. It looks like this. Hold on 1 second. So it has, where's my pen? It has this asymptote. It's going to continue really close to that asymptote and then up and over. That's the shape of the log, and no matter how far down you go, this thing would still be going down there. The asymptote for natural log of x is at x equals 0. We are on logs, so it's vertical, x equals 0. And it looks fine on the calculator screen. I think you could kind of see what was happening there. Let's try this one though. The natural log of x minus 3, and the x minus 3 is all contained inside that grouping. So my calculator, I would type in the natural log of x minus 3, and then I gotta make sure I end that parenthesis. So I have my function typed in, and I hit graph, and it looks like this. Well, it looks like I need to get my screen so I can write on it again. It looks like instead of having this asymptote over here, I'm going to shift that over. It should look like this, but for some reason, with the asymptote also shifted over at a new value, x equals 3. But for some reason, and this is maybe what it should look like on your calculator, for some reason the calculator has decided that it looks like, whoa, that was so weird. I didn't know it would do that. That was pretty exciting. Got extra graphs now. For some reason the calculator shows it almost as if it has a starting point here, like a square root, but it does not. You need to know, and you need to be smarter than your calculator. You need to know that that does not have a starting point. It has an asymptote. And even though your calculator screen looks like that, you know that that function does have an asymptote there. Okay, so when you looked at the screen on the calculator, you could see the asymptote was at positive 3. Remember, it's usually over here at 0, so in this function, it's shifted over 3. The function itself has this same shape of this really light dotted one. And you could graph it. I think as you're graphing logarithms, it's really handy. One handy thing to do is to look at the table. So you use the second button and hit that graph button again to get the table. It didn't work. Second table. There we go. And you can usually find one nice point right here, the point 4, 0. That is just a really nice integer point on the graph. And you can see that it's right here, 40. I made sure I hit it. Okay, so it's really close to the asymptote, goes through that one nice point, and then we'll continue growing after that. The domain of a logarithmic function is very much limited. It is not all real numbers. And we saw that earlier when we tried to evaluate the log of -3. It didn't work. Our calculator said that there was an error. The domain of this function is just everything to the right of wherever that asymptote is. It's from 3 to infinity in this particular case. And we would not include the 3. It would be a open parenthesis here. And then the range, if we're thinking about range, we often think of that in interval notation as bottom to top, bottoms up. Range of this log equation is -infinity to +infinity. Okay, we're going to look at 3 more graphs. This one is the natural log of x plus 4. Now, on this equation that is written here, I don't have grouping parentheses here because it's sort of understood without those grouping parentheses that the only portion of that expression that is included in the log, if you will, is the x. So it's the natural log of x, and then you add 4. So this is a little different from the one we looked at just barely. So if I want to graph that, y equals, it's the natural log of x, and I need to tell the calculator that's where the log ends. So you've got to close the parentheses, and then you can add the 4. And when I graph that, I can see that the function, that logarithmic function, shifted up. It's got this asymptote here at 0 and then curves up and over. If we look at the table, we can find one of the nice points on that graph. It's right here, 1, 4. So let's graph that on our coordinate plane. 1, 4 was that nice point. We had the asymptote at 0. So the function kind of goes up really close to that asymptote, over through that point that we found, and curves up, continuing to grow. The domain of this function is from 0 to infinity, and the range is from -infinity to infinity. Remember, domain is your x values, range is your y values. 2 more. H of x is the natural log of the quantity x plus 1, and then we subtract 3. So when we type in our calculator, make sure you get the end parenthesis where you need it. It's the natural log of x. I gotta look again. Plus 1 minus 3. Plus 1, end those parentheses, minus 3. And if we graph that, we can see that it went to the left 1 and down 3. If we look at our table, you can see this nice point here at 0, -3. So let me go back to my coordinate plane. 0, -3. That was my nice point. The asymptote, well, this function shifted back 1, so the asymptote is at -1. So the function is really, really close to that asymptote, curves up over through that point. The domain in this case would be from -1 to infinity, and the range is -infinity to +infinity. Last one, negative natural log of x plus 2. So if we use our calculator to help us graph that, it would be the negative natural log of x. Oh, got some other stuff here. Okay, and then that's all for the log. So we need to end that parenthesis and then plus 2. Let me make sure. Yep. So remember that it's sort of understood that only that x is part of that log because there weren't any other groupings. So we've got it typed in right. If I look at the graph, this is interesting. Because of that negative in front of the log, it flipped it over. So instead of going up and over, it sort of goes down that asymptote, really close to the asymptote, and then curves over. If I look at the table, I can snag a nice point off of that. 1, 2 is a nice point there. So we've got the point 1, 2. The asymptote is at 0. It didn't shift left or right. It just shifted up 2. So our function sort of comes down and over. The domain here is from 0 to infinity, and the range is from negative infinity to infinity. So that is it. You now know what a log is. And at first, sometimes they seem a little weird or confusing, but you'll get the hang of it. We'll practice a lot. They're kind of fun in some ways because they're quite a bit different from other things that you've done in the past. Come in and get help if you need some help, but that is it for this lesson. Thanks.